This video is part of the series of videos related with the book Statistical Modeling with R that I wrote and was published by Oxford University Press in 2023. In today's video, I'm going to talk about a generalized linear mixed model with a binary response variable that corresponds to a randomized block design. Starting as always with an exploratory data analysis, to be followed by the frequentist model fitting and the Bayesian model fitting. The codes and data to run this analysis are in the website shown in the screen. So the goal of the analysis is to predict the probability of parasitism, the incidence of a nematode that parasitizes deer of both sexes in Spain, according to the mass of the animals. So I started by importing the data. Here is the sex of the animals, the length, the body size of the animal. The presence or absence is a binary response variable with a minimum of 0 and a maximum of 1. And here farm records the provenance of the animals sampled. So deer come from 24 farms, and it's reasonable to presume that individuals coming from the same farm share a common set of experimental conditions that are peculiar to each farm. That is, deer coming from a given farm are not statistically independent replicates of the values of the response variable, since that they are correlated is because they share a common set of environmental conditions. Here I depict the number of animals according to the presence or absence and the provenance, that is the farm of the origin. We see that we have a very unbalanced sampling of individuals across farms, and this would be even more so when we discriminate for sex. For instance, we can notice that from a certain farm we only have one animal. From another we have 3 animals in total. From others we have 26 or more than 200 animals. So it's a very uneven sampling of animals across farms. Needless to say, for those farms for which we have very few data points, for instance these and a few others, we could not possibly aim to fit a binary GLM with such a small amount of data, number of data points. So the exploratory data analysis, we explore the relationship between the response and explanatory variables overall, and here I sampled the body size standardized in order to have a 0 mean and unit standard deviation. So 0 here corresponds to the average body mass for females and for males, and so we see that there is indeed a relationship as depicted by these fitted GLMs with a different relationship for males and females. Then if we explore the relationship between these explanatory variables and the responsive variable only for those farms with more than 13 deer, these are 3, 4, 5, 6, 7, 8 farms for which we have more than 30 deer, not necessarily of both sexes, but in total more than 30 deer. And here we see that the type of relationship varies as signaled by this fitted GLM at the farm level, varies significantly in both slope and intercept across farms. So the frequentist model fitting, the statistical model is that the response variable follows a binomial distribution, the only possible distribution whenever we have a binary response variable coded as 0s and 1s. And for each sex, we would estimate the logit of p. This is a link function. Beta 0 and beta 1 corresponds to the fixed effects, fixed or population level effects, and b0 corresponds to the to a coefficient depicting the departure of each farm from the global relationship between the global value of the intercept, and B1 corresponds to the random effects, in this case the random slopes depicting how much each farm departures from the population or fixed level effects. So we fit the model, so the fixed effects are going to be sex and length under interactions, and the random effects are going to be the variations of slopes and intercept that are assumed to be the same for both sexes. This variation will be across farms. So the fitted model is the presence, absence, the binary response variable, sex and length, both in the both in the single effect and their interaction. These are the fixed effects variables, and here we have the random effect variables defined by the categorical variable farm. So the one here indicates that we are going to estimate the random intercepts. This is the V0 coefficient, and length here denotes that we are going to fit random slopes, that is the variation of the slope of each farm with respect to the fixed level effects. So the summary of the model shows the variance, or if you wish, standard deviation. Let's focus on the variance for a moment. The variance of the intercepts across farm and the variance of the intercepts across farms, and the correlation between the two. We notice that the variation between intercepts is about 8 times bigger than the variation among the slopes across farms. So here in what is called the conditional model, we have the intercept. Sex is a categorical explanatory variable. Male here indicates that female is the sex of reference, and so we have the intercept here corresponds to the intercept of for the reference sex, the females, and 1.39 corresponds to the slope in the space of the log-link function for the females. For the males, we have these are the differentials of intercepts and the differentials of slopes. In both cases, the intercepts and the slope for males are obviously smaller than females. This coefficient here is the difference between intercepts between the reference sex, females, and the other sex, males, and this p-value here says that this difference happens to be statistically significant, if you're interested in that. The statistical significance of the value, this is the length. The length is a numerical explanatory variable, so this is the length. This is a slope corresponding to the females, the reference sex, and this p-value here simply says that there is a relationship between this numerical explanatory variable and the logit of the probability of the logit of parasitism. So delving further, let's have a look at the fixed and random effects. So here are the coefficients for the fixed effects, the intercept and the slope for the reference sex, and the differentials of slopes of intercepts and slopes for the other sex, in this case male. And you also have order here in increasing terms of its magnitude, the differentials of the random intercepts, denoting how much each farm deviates from the in its intercept. So we see that for a certain number of intercepts, for a certain number of farms, these deviations are negative. For other farms, these deviations are positive. Notice that the scale for the random intercepts goes roughly between minus 2.5 and plus 2.5, whereas the scale of the random slope is a lot smaller, in consonance with the previous what was shown in the previous slide of the variance of the random intercepts and the random slopes. So here are the fixed effects, the actual relationship for the relation between the length and the logit of p, the probability of parasitism, for the females and for the males. We also obtain the conditional and marginal R squared. The marginal R squared is a proportion of the variation of the response variable explained by only the fixed effects, and the conditional is a proportion of the variation of the response variable explained by both fixed and random effects. The difference between the two corresponds to the proportion of the variation explained by the random effects, which here is clearly prevalent for this data set. So in order to assess the goodness of fit of the model to the data, we use the package Mixed that is adequate for the model fitted with the package GLMM. To gather the input for the residual analysis, here is the basic input for the residual analysis. Here we use the package Dharma to simulate the results of the obtaining the Dunn-Smyth residuals that here are converted to a normal distribution and stored in the original data frame. With this data, we obtain the following plots. So there's a series of 8 plots. First of all, we plot the residuals against the fitted value. We see more or less a random scatter. We don't see any trend or any obvious departure from randomness, neither in this plot A nor in the plot B that plots the residuals, the transformed Dunn-Smyth residuals against body length. Here we see the cooked distances, and we see that very few points have a relatively large cook distance, none of which is very much higher than the others, so there is no point that happen to have a large influence on the fitted values of this GLMM. So in terms of the importance of the farms, we see that there is one farm here called MB that happens to have a large influence on the values of the fitted parameters. We see that the residuals are all follow a normal distribution as indicated by that indicates a very good fit of the model to data, and the random intercepts and the random slopes, here we have 24 points, one per farm, both follow a normal distribution, and then the AUC that can also be computed both for this type of models as for any GLM with a binary response variable shows a value of 0.86, indicating that this model taking a random set of zeros and ones, this model correctly predicts 86% of the observed presences or absences of parasitism. All in all, this analysis shows that the model has a very good fit to the data. In order to communicate the model results, besides the fitted parameters under 95% confidence intervals, we could obtain the conditional curves using the package GGFX. We obtain those for only the fixed effects and for both fixed and random effects. This is why the width of the confidence band is much larger in plot B than in plot A. By and large, here we see that the relationship varies according to the sex, which is consonant with the statistically significant interaction that we found beforehand. So the Bayesian model fitting, again, the response variable follows a normal distribution, and for each sex we show the same relation that was discussed before for the Frequentist model fitting. This is the population level intercept, this is a population level slope, and these are the farm level departures of intercept and the farm level departures of slopes. These are the group level effects, or rather we could refer it in the following way. This is the slope for the reference sex, this is the differential of intercept at the population level or fixed level if you wish. For the overall relationship with for the overall intercept, these are the farm level departures from the population or average level or our average relationship. Again, this is the slope, this is the intercept for the reference sex, and this is the differential of intercept between the reference sex and the other sex, and these are the population level coefficients, the group level coefficients depicting the departures from the population level effects at the level of each farm. So we get the priors all in the link scale, and we again see those related with the population or fixed level parameters. Here is the intercept, here is the slope for the reference sex, here is the differential of of intercepts between the reference sex and the other sex males, and here is the differentials of intercept, the population level difference of the population level differential of slopes between the reference sex and the other sex males. We also see the parameters for the group level effects. These are the standard deviations of the B0 and B1 coefficients at the farm level for the intercept and the slope. Here we see the prior for the correlation between the group level intercept and the group level slope. So I simply here define normal on an arbitrary basis without much thought, specific prior for certain coefficients of class B. This is the population level parameters for certain parameters, in this case the differentials of intercepts and the differentials of slopes, and another prior for the Lewandowski et al. Distribution for the modeling the correlation between the slope and the intercept. So in the book I hasten to point out that in the book I compare models with different random or group level effects for both Frequentist and Bayesian frameworks, and I chose to omit this comparison for the sake of brevity in this video. So please have a look in the book if you want to see more of that. So I fit the model, and the model is with this formula that is the one shown before. The priors that I showed before, number of chains, the warm-up and the number of iterations, family equals Bernoulli, because we have a binary response variable, and here we have as output the marginal posterior distributions of all model parameters in the logit link scale for the population, for the group level parameters, or for the population level parameters. Here are the posterior distribution for each of the parameters. This is the mean, the standard deviation that here corresponds to the standard error of for each of these parameters, and the 95% credible interval for each of them. We said that the R-hat coefficients are all equal to 1, and that we have a large number of sample values in all the chains, statistically independent large number of sample values in each of the chains, suggesting that the model has indeed fitted very well to the data. For the population level parameters, we see that for taking for instance the slope for the reference sex, the value is the mean value is 1.45, and there is a probability of 95% that the value of this slope ranges between 0.94 and 2.1, which is and obviously we see that it's highly unlikely that 0, showing the absence of relationship between length and the logit of p, is included in this credible 95% credible interval shown here. So we can obtain the posterior distributions to see the convergence of the main parameters for each of the chains. We indeed see that all chains have converged to the same common posterior distribution, and that the model explains 34.7% of the data. This is the Bayesian R-square as suggested by Gelman in the paper by Gelman et al. Of 2018. We also can verify the convergence of the chains, not only for the group level effects, for the population level effects, but also for the group level effects. Here is for the slopes. We can also obtain this is for the group level differences of slopes. So we see that for each of these group level differentials of slope, the parameters B1 in the previous slide, that we not only obtain a posterior distribution, marginal posterior distribution for each of them, but that these posterior distributions have converged for the 3 chains to the same common posterior distribution. So we can also assess the autocorrelation of the estimates only for the main parameters of the models, and we see that perhaps with the exceptions of the intercept of the reference sex, and for these standard deviations at the group level, by and large we have a large number of statistically independent values sampled in each of the chains. If we want to fix this small problem of the relatively large correlations of 0.4 or so between estimates separated by 2 or 3 steps in the chain, we could increase the thinning rate at the moment of fitting the model. This was discussed in previous videos in this series, and of course also in the book. In order to assess the goodness of fit of the model to the data, we use the Dunn-Smyth residuals that can be calculated with the package Dharma based on the posterior predictive distribution. So here is the posterior predictive distribution obtained from the fitted model m2.brms, and with the command create Dharma of the package Dharma, we obtain the Dunn-Smyth residuals that are converted to a normal distribution. I again reiterate that these converted Dunn-Smyth residuals will only have a normal distribution if the model fits well to the data. So now what we do is that we create a data frame with all necessary input for the to make the plots for the residual analysis, and this input includes the previous residuals, the explanatory variables, the fitted values, the average values of fitted values, and the Pareto K coefficients that are analogous to the Cook distances in that they indicate the importance of each point to the fitted to the posterior predictive distributions of all model parameters. With this, we obtain the plots, and here are the plots. Here we in the first 2 plots A and B, we plot the residuals against the average of the fitted values, and the residuals against the body length, the standardized explanatory variables, and we see indeed a random scatter in both points. In plot D, we see that the converted Dunn-Smyth residuals do indeed have a normal distribution, as indicated by that would suggest a very good fitting model. We also see that in plots E and F that the group level differentials of intercepts and of slopes do indeed have a normal distribution, and the Pareto K coefficients, we see that all points but 3 are in a very good range, suggesting that the posterior distributions are by and large insensitive to each of the deletion of each of these data points. There are only 3 points only in the good part. So by and large, this is a model that has an excellent fit to the data. We can, to communicate the model outputs, we can obtain just one PP check. This is obtained using a function that we define. This function is called presences. It's called the proportions. It will allow us to estimate the probabilities of obtaining the incidence of parasitism. This is the PP check calculated over the posterior predicted distribution for 1000 values, and this is the observed incidence of parasitism. What this shows is that by and large this model predicts, as a typical realization, the observed value of parasitism. These PP checks obviously can be extended to other features, both at the population level and at the group level. We also obtain a posterior distribution of the area under curve, the AUC, and we observe, because we obtain a posterior predicted distribution, we can calculate a mean. The mean of the AUC, please have a look at the book on how this is calculated, because it doesn't arise automatically from the fitted GLMM at the Bayesian, using a Bayesian framework. So because we obtain a posterior predicted distribution, here it is of the AUC, here it is, we can obtain a mean, here's the mean. Okay, we can also obtain a 95% credible interval for this this AUC, this area under curve. We can obtain the conditional curves with only the population level effects, and for both the population level and the group level effects, which is why these bands are much wider in plot B than in plot A. And here I simply show, among the many interesting features of the output obtained in the Bayesian fitting of a GLMM, I show the posterior distributions for the group level intercepts and for the group level slopes. Notice that the average value of these distributions are very different from each other, and some are wider, some are smaller. This is all related to the number of data points. The width is related to the number of data points in each of these farms or groups. So in this video, I have explained the fitting of a generalized linear mixed model with a binary response variable and something akin to a randomized block design, starting with the exploratory data analysis and followed by the Frequentist and Bayesian model fitting. I hope you found this video interesting, and I recall that the data and codes to run this analysis can be found in the website shown on the screen. Thank you for your attention.